Hey everybody, Matt from 90th percentile.ca here. For access to more study notes, practice questions, mock exams, and end of chapter question videos, visit 90th percentile.ca and sign up for your free trial today. Link below in the description. This learning module is hypothesis testing. It's a pretty important module. There's almost guaranteed to be something on the exam related to hypothesis testing, so we're going to make sure go through it step by step and understand the main two topics that I have written here. First one being the steps that we need to take when conducting a hypothesis test. So these steps are always the same, regardless of what different type of test you're using on the right-hand side here. So the steps are always the same. There's some small differences in step 3 and 4 here, but we'll get to that in a second. First step, always to state your null and alternative hypotheses. So you're testing the null, and you are either going to reject or not reject the null hypothesis in exchange for an alternative hypothesis. Step 2 would be to decide on a significance level, which would in turn affect your confidence interval. And this decides what your critical value is going to be, by which you decide whether to reject or not reject the test. The critical value, I've kind of mentioned it a couple times now. Depending on what test you're using, all of these values in step 3 are going to be different for the critical value. On the exam, you should already have these 3 steps given to you in the question. Like the critical value, we've kind of touched on it, where, for example, in a t-test, you got to like look through a table and figure out the degrees of freedom and the confidence interval and all that. I highly doubt that's going to happen on exam day. You're usually just given the critical value regardless of what test you're using. So just something to keep in mind how significance level affects your critical value, but these first 3 steps should already be given to you. And then what's really important and is usually the first thing that we need to do is to calculate the test stat depending on which test you're using. So in 3 and in 4, both of these values are going to change depending on what type of test you're using. There's a bunch of different formulas that we have to calculate test stats for the different type of tests. Some of them get really, really messy. Like if I'm just looking at this list here, I'm going to highlight these 2 for now because these are most likely to show up on exam day. We'll talk about the other ones in a little bit, but just one thing to note is that depending on which test and which distribution you're using, you're always going to have a different formula to calculate your test stat. And then finally, once you have 4 and 3, these are the most important, you make your final decision as to whether reject or not reject the null. And your decision to reject or not reject is dependent on, 1, comparing your value in 4, so your test stat, to your value in 3, your critical value, but it also depends on whether or not the test is two-tailed or one-tailed. So an example of a two-tailed test would be something where, the null is that the mean is equal to 6. And this is two-tailed because our alternative is that it's not equal to 6. So it can either be, different than 6 on the positive side or on the negative side. So either way, that the information shows us that the mean might be different. If it's on the negative side or the positive side, we can reject on 2 sides. And our decision on whether or not to reject is based on if this test stat that we calculate using our formula in step 4 is outside the critical values that were provided. So I used, like an absolute value of the test stat being greater than the absolute value of the critical value. Another way to think of it would just be that it's outside. So like if I have a critical value of, let's say, negative 2.5, and my test stat that I calculate is negative 2.7, this is outside of the negative 2.5, and the absolute value is also greater. So like positive 2.7 greater than positive 2.5. So just 2 different ways to think about it. It's a little bit different for a one-tailed test because here the alternative hypothesis could be that the mean is greater than 6. So here we're only worried about the right side, about the mean being largely greater than 6. We don't care if it's less than. So we're only concerned about the right side. And in the case of a one-tailed test, if we use the example of a left test, which is a little bit different than this, so we're just worried about the alternative being less than, you're going to reject the null if your test stat in step 4 is less than your critical value in step 3. And one quick thing to note is that whether or not it's a left or a right-sided test depends on the alternative hypothesis. So it's not based on the null, it's based on the alternative. So in this case, I have the alternative is less than 6, so it's a left-tailed test. If the alternative, like I said up here, was greater than 6, then it's a right-tailed test. So just quick summary, we're going to go over all these steps in detail, but most important thing to note is that steps are exactly the same, except the values that you get in step 3 and 4 are going to be a little bit different. So moving on to the different type of tests, there's 6 different ones that the curriculum provides. One is when you're testing a mean or the value of a mean. 2 is when you're testing the difference between means. So you could have like a null is at mean 1 less mean 2 is 0. So you're effectively saying the null is that they're equal. So when you have 2 different means and you're determining whether or not they're different, there's another type of test for that. These 2 up here, like I said, are the most common to show up on exam day. And depending on what you're testing and what information you're provided, you're going to either use the Z or the T distribution. So if you're testing a mean, you're either going to use Z or T, depending on whether or not you know the population variance or what the sample size is. Once again, we'll flush that out a little bit later in the questions. For the mean difference, you're always going to use a t-test. It's just one of those things that you have to know. And then these 4 tests down here, we'll go over a chi-square test really quickly. But like I said earlier, the test stats and the formulas to calculate the test stats for these tests are, I mean, for 3, 4, and 5, they're provided in the textbook. The formulas can get really, really messy, and from my experience, they're not common to show up on the exam. What's more important is to know when to use them. So, like if you're testing the value of a single variance of a population, use the chi-square test. If you're testing whether or not 2 variances are different, use the F test. If you're testing correlation, you're going to use either a t-test or a Spearman rank test. Once again, depending on the like small details that are provided regarding correlation. And then the last one is non-parametric test, which we don't even have the formulas in the textbook for calculating the test stats. So it's just more for this, especially, is just knowing when to use them. But like quick summaries that these non-parametric tests are testing anything that's not a parameter of a population, and a parameter of a population is something like a mean or a variance or a correlation that can be used to describe the population. So anyway, like I said, we're going to spend most of our time on the first 2 here, and we're going to take the steps on the left-hand side to conduct Z and T tests. We'll go over a chi-square test really briefly at the end. But like I said, really got to focus on these 2 and make sure that we really understand them. So with that, let's go into the questions.
Which of the following statements about hypothesis testing is correct? A, the null hypothesis is the condition that researcher hopes to support. That's not true. We want to make sure we have no bias when we're coming into these hypothesis tests. B, the alternative hypothesis is the proposition considered true without conclusive evidence to the contrary. That's actually the null hypothesis is considered true, and we need some level of significance in order to reject the null and take the alternative as true. So our answer is going to be C, which is the alternative hypothesis exhausts all potential parameter values not accounted for by the null. So we can actually show an example here. We have H naught, or the null, is that the population mean is equal to 0. On the flip side of this, the correct alternative hypothesis would be that the mean is not equal to 0. So it includes every possible value other than 0. So our answer is C.
Starting with this one, Wilco is a manufacturer in a mature cyclical industry. Who cares? During the most recent industry cycle, the net income averaged 30 mil per year with a standard deviation of 10 mil and 6 observations. So we have the sample mean 30 mil. The sample standard deviation is 10. I'm using the notation for the sample standard deviation because this is going to be a t-test. You can tell because it's 6 observations. As we run through the calc, like you could, even if you assumed it was a z-test by accident, you'll notice that it doesn't make a difference. But we'll just go ahead with that. Continuing along, management claims that Wilco's performance during the most recent cycle results from new approaches and that Wilco's profitability will exceed the 24 mil per year observed in prior cycles. So in A, with mu as a population value of mean annual net income, formulate null and alternative hypotheses consistent with testing Wilco management's claim. So we need to set up. Let's do it over here. So for A, we have to set up the null and the alternative hypothesis. So the null is going to be that the population mean is less than or equal to 24 mil. And the alternative is that it is greater than 24. So it's a bit weird. That when you're reading this, you're saying management claims that Wilco's performance during the most recent cycle results from new approaches, and that Wilco's profitability will exceed 24 mil per year. So you have to align your beliefs or what the management is saying with the alternative, because we're not, once again, hypothesis tests are worried about rejecting or not rejecting the null. That's like the official interpretation of what you're doing. So even though we're concerned with exceeding 24 mil, we don't actually accept the alternative hypothesis. We have to reject the null. So by rejecting the null, we are not officially accepting, just kind of a weird like terminology thing. But by rejecting the null, we're saying that it will exceed 24 mil at some significance level. So it's kind of just flipped of what you would think. It's a little bit weird, but let's go with it. For B, assuming that Wilco's net income is at least approximately normally distributed, identify the appropriate test statistic and calculate the degrees of freedom. I'm having trouble saying that today. So what are we doing? We got to identify the distribution and the t-stat that we're using, and it's going to be the t-test because we're assuming it's approximately normally distributed. We have less than 6 observations. So we're going to be using the t-test, and to calculate the stat that we're going to compare to the critical value, the formula is x bar minus the hypothesized mean over the standard deviation divided by the square root of n. We plug all our stuff in from up here. We have 30, which is our mean that we observed, versus the hypothesized mean of 24 divided by the standard deviation, which we have is 10, divided by the square root of 6. And if we run this calc out, we get 1.47, around that. And now we're going to have to compare this to the critical value. So see, once again, this is what I was saying about how they usually just give you the critical values. You don't have to like go through a table. But anyway, so we have our statistic of 1.47, and it's a one-tailed test. And the critical value is 2.015. So what we calculated is less than the critical value. So we do not reject the null. One more quick point on this one is going back to what I said earlier about if you didn't recognize that this was a t-test versus a z-test, the conclusion you would have came to would have been the same. Like the notation here would have been a bit different. But if you recall, the formula for the test statistic for t is this versus for z, a z-test, it's the same thing pretty much, but we just have the population standard deviation. So this is the difference here with this. And of course, the critical value would be different too, depending on if you're doing a z-test or a t-test. But the critical value is actually given to you in this question, so it wouldn't have mattered which one you use, whether it's the t-test or the z-test, you would have came to the same conclusion.
Which of the following statements is correct with respect to the null hypothesis? A, it can be stated as not equal to, provided that the alternative hypothesis is stated as equal to. Get back to that one. B, along with the alternative hypothesis, it considers all possible values of the population parameter. So this isn't true. So we can have, let's say we have a hypothesis. Like if it considers all possible values, I mean, it just doesn't make any sense. It would assume that population mean could be anything, like all values, and the alternative is the same thing. Like you're not testing anything here. That doesn't make any sense. These two need to, the criteria that you're stating for both the null and the alternative need to be mutually exhaustive. They need to be effectively the inverse of each other. So B is incorrect. Let's go to C. In a two-tailed test, the null is rejected when evidence supports equality between the hypothesized value and the population parameter. So if we say like a two-sided test would be something like this, where we have the null as the mean is equal to 6, then the alternative would be mean is not equal to 6. This is two-sided because, let's say the 6 here. If we have enough evidence to support that the mean is not equal to 6, it can either be not equal to on the on the negative side or on the positive side. It could be like negative 12 or positive 12. Either way, it's not equal to 6. So the two-sided test accounts for basically both sides of this. So coming back to C, the two-tailed test is rejected when evidence supports equality between the hypothesized. So they're saying the test confirms that the mean is equal to the hypothesized value. So in that case, you would not reject the null. You would consider it true. So this is false as well. The answer is A. I wanted to come back to this for a reason. The null is typically set to like the population mean is equal to something. It's just the way it normally is. I mean, technically you could have it switched here where you have the null is not equal to 6 and the alternative is equal to 6. The point they're trying to get across is that the null and the alternative have to account for every possible event or every possible outcome that the population mean actually is. In practice, you would usually see the null being equal to and the alternative being not equal to. I guess you could have it the other way, but in practice, it's typically the way I just said, with the null equal to. You wouldn't really see it any other way. You could, but once again, they're trying to make stuff a little bit more complicated than it should be. Which of the following statements regarding a one-tailed hypothesis test is correct? A, the rejection region increases in size as the level of significance becomes smaller. So remember, the confidence interval is 100 times 1 minus the significance level. So if we started off with a significance level of 0.05 or 5%, this would be a 95% confidence interval, which we have right here. So if we decreased this significance level to, let's say, 1%, the confidence interval becomes 99%, and the rejection region would be outside of this confidence interval, so it would actually be a smaller rejection region. So this is incorrect. B, a one-tailed test more strongly reflects the beliefs of the researcher than a two-tailed test. This is actually the answer, and the reason why. Take two alternative hypotheses. So one is that the mean is greater than or equal to 6, and the other alternative is that the mean is not equal to 6. Here, we're not worried about the values being less than 6. We're pretty much being confident that it's not less than 6, whereas here, it could be, anything. It could be on either side. So the researcher is just ignoring this side with the one-tailed test, which means that the researcher is more confident in what the results of the test will be. C, we can look at it anyway. The absolute value of the rejection point is larger than that of a two-tailed test at the same level of significance. So this is incorrect. For a one-tailed test, the way to kind of think about it is this chart here is a two-tailed test, so we can either reject on this side or on this side. For the same level of significance, so let's say significance is 5%, for a one-tailed test, this entire red shaded area would just be shifted to one side and would be ignored on this side, which means this would come out further to the right on a left-sided test, and this value or the critical value would actually be less than the value for the two-sided test. So it might be like, negative 1.5 or something like that. So that's incorrect. The answer is B. Three questions that we can hammer off here at the same time. 6, the value of a test statistic is best described as the basis for deciding whether to reject the null, accept the null, or reject the alternative. So we never reject the alternative. That's not the focus of the hypothesis test. It's always on rejecting the null. And you could also think, if we don't reject the null, we technically accept it, but it's just not the terminology that's used for hypothesis tests. It's even though we don't reject it, we don't officially accept it because we're only using like a 99% confidence level or something like that. So don't officially accept it. The focus is always on either rejecting or not rejecting the null. Which of the following is a type 1 error? A type 1 error, I have some visuals and some definitions over here. So a type 1 error is rejecting the null hypothesis when it's true, which is, it could also be known as a false positive. So if we have a 95% confidence interval, we are 95% sure that we will make the right decision regarding the null hypothesis. And on the flip side of that, the 95% confidence interval reflects a 5% significance level. So there's a 5% chance of a type 1 error. So we're 95% sure in the confidence interval, so there's a 5% chance that we're wrong when we reject the null when it's true. So type 1 error is also equal to the significance level. And 7 is A, rejecting a true null. And then 8, a type 2 error is best described as, well, you can see over here, a type 2 error is not rejecting the null when it's false. So this is a false negative. You can kind of see the visual down below. We have the type 1 error here, which is equal to significance level. The type 2 error is a bit more complex. It's measured by beta, and the actual calculation of this is very stats heavy. It's outside of the scope of the CFA curriculum, but all you have to know is that type 2 is a false negative. So don't rejecting or failing to reject a false null, so B. And as another point, just to kind of hammer this down, if we were to decrease the significance level, we're going to decrease the probability of a type 1 error because type 1 is equal to the significance level. The probability of a type 1 error is equal to the significance level. And on the flip side, a decrease in the significance level is actually going to increase the probability of a type 2 error, because if we're decreasing the significance level, it makes it harder for us to reject anything. And a type 2 error is not rejecting it when it's false. So if it's harder for us to reject something, then we're more likely to not reject the null when it's false. The probability of correctly rejecting the null hypothesis is the p-value, power of a test, or level of significance. So let's start with C, level of significance, which we know is equal to the probability of a type 1 error. And a type 1 error is rejecting the null when it's true. So if we're correctly rejecting the null, that means the null must be false. Well, a type 1 error is related to when the null is true. So the level of significance is not the answer. For p-value, I'll come down to this chart. Let's say we were doing like a one-sided test with a 95% confidence level, which translates to a 5% level of significance. And our z value was over here. And we rejected the null, right? So we rejected it, which means that the test statistic that we calculated was somewhere over here, somewhere to the left of this. There might be some room like within here where we could have had a lower level of significance and consequently a higher confidence interval where we could have rejected the null. So the p-value effectively represents the lowest level of significance, which shifts it out further, at which we can reject the null. So p-value is not correct either. And the answer is going to be B. We'll talk about it now. So the probability of correctly rejecting the null hypothesis is the power of a test. And the power of the test is actually 1 minus beta, which is the probability of a type 2 error. So for a type 2 error, we're failing to reject a false null. Failing to reject. So the opposite of that would be correctly rejecting a false null, which is exactly what we're doing here. So the answer is B. And then 12, the power of a hypothesis test is exactly what I just said, the probability of not making a type 2 error. This is a good question here. It really helps us practice whether or not we are correct when we're rejecting a null and the steps that we need to take to either reject or not reject a null given some certain values. So for each of the following hypothesis tests concerning the population mean mu, state the conclusion regarding the test of the hypotheses. So for A, null hypothesis that the mean is equal to 10 versus the alternative that it's not equal to 10 with a calculated t statistic of 2.05 and a critical t-value or critical t-values because it's two-sided of 1.984. So this 2.05 is actually already given to us, but normally we would have to calculate the t-statistic by taking the sample mean that's given to us in the calc, subtracting the hypothesized mean, which is 10 in this case, and dividing it by the sample standard deviation, divided by the square root of n. T-test, of course, uses the sample standard deviation because we don't know the population mean or the population variance, and the z-test statistic is the same thing, but the only difference is that we have the actual population standard deviation here. Anyway, we can draw A on a chart right here. So we have critical t-values. You wouldn't really have to do this. I'm just using it as a visual. So critical t-values of negative 1.98 and positive 1.98. So we would have ran this formula here, and for right now it's given to us, of course, we get 2.05, which is beyond this 1.98, so we have 2.05 beyond this, which means that given the information we have, we are in the rejection region. We have enough data to reject the null because we're beyond this. So we can reject this one. We're coming to the next one. This is a one-sided test. So mu null is that the mean is less than or equal to 10 versus the alternative that is greater than 10. We have a critical t-value of 1.679, call it 1.8 or 1.68, and a calculated stat of 2.35. So we're like way over here. So we definitely have enough room to reject the null. So we do. Also note that on a one-sided test, when the null is at a value is less than or equal to a certain value, the proof that you need is going to be on the right-hand side. So when the value is definitely greater. Next, for C, the null is that the mean is equal to 10 versus that the mean is not equal to 10. We have a t-stat of 2.05 and a p-value this time of 4.6% and a level of significance of 5%. Remember what I said earlier I believe is the last question of the one before. The p-value is the lowest level of significance that we can reject the null. So given that the p-value is less than the level of significance, there's some room here. There's like, 0.37% of room to be able to reject. So it might look something like this. It's not exact. I'm just going to use this side of the chart. Even though this test is two-sided, it would look kind of something like this, where we might have a z or a t critical value of like negative 2.1, and the p-value is like somewhere over here. So that means this little bit of room is the extra leeway that we have to reject the null with a lower level of significance. So anyway, we reject here. For D, we have a null that the mean is less than or equal to 10 versus the alternative that is greater than 10. We have a 2% level of significance and a calculated test statistic with a p-value of 3%. So here the p-value is greater than the significance level, which means that we do not have enough proof to reject the null. So we do not reject. Just the exact opposite of C. Hope that cleared it up. This is pretty important. Like I said, almost guaranteed to be on exam day. One of these variations, we don't know which one, obviously, but got to make sure we really get this down and understand it. I just drew this visual as a guide, but on exam day, you should just be able to know that test statistic is greater or less than the critical value for a two-sided test, or greater than on a right-tailed hypothesis test, or less than the value on a left-tailed hypothesis test. We should reject, and then the p-values can also be incorporated as well. A couple more really quickly on p-values. Which of the following statements on p-value is correct? Let's go from the bottom, because I was just explaining this earlier. The p-value is the smallest level of significance at which the null can be rejected. This is true. We can just go through the rest of them right now as well. So for B, the lower the p-value, the weaker the evidence. That's incorrect, because the lower the p-value represents the lower p equals the lower level of significance, which is a higher confidence interval at which you can reject the null. So there's stronger evidence, not weaker, stronger. And A, the p-value indicates the probability of making a type 2 error. It does not. It's more related to type 1 errors, but even then, like, the probability of the type 1 error is the significance level. 20. The following table shows the significance level and p-value for two hypothesis tests. In which test should we reject the null? So we have significance level and p. Test 1 is a two-sided test. Not that it really matters when you're comparing significance levels and p-values, but anyway. Test 1, significance level of 0.02, p-value of 0.05. So given that this is the lowest significance level at which we can reject, and the significance level is lower than the p-value, we do not reject. Well, for test 2, it's the exact opposite. The numbers are just switched. Significance level is 5%, but we could reject it at a 2% significance level, which shifts it out even further on the graph. If this was the z-value, and this was the p-value at 0.02, this was the z-value at 0.05, you can see that we have this extra room at which we can reject. So we're going to reject here. So the answer is reject B, test 2 only. An analyst is examining a large sample with an unknown population variance, so automatically not a z-test. Which of the following is the most appropriate to test the hypothesis that the historical average return on an index is less than or equal to 6%? So the null is that the mean is less than or equal to 6%. So this is not a two-sided test. This is a one-sided test because we're only worried about one side. So you can automatically scratch out this answer, which is a two-sided t-test. Now our remaining answers are a one-sided t-test or a one-sided chi-square test. Haven't brought it up yet, but the chi-square test is used to test a variance of a population, not a mean. So in the case of you're testing a variance, you would use this, but in this case, we're worried about the average return, which is a mean. So the answer is a one-sided t-test. Which of the following tests of a hypothesis concerning the population mean is most appropriate? A z-test if the population variance is unknown. Nope. Z-test always has to have a known variance. B, a z-test if a population is normally distributed with a known variance. Yes. This is exactly when a z-test is used, but we can look at C anyway. A t-test if the population is non-normally distributed with an unknown variance. So we're good so far, but we have a small sample. So that's why you cannot use the t-test here. You can use a t-test for a population that's non-normally distributed, but you need a large sample size to make the sample distribution approach normal. Remember, with more degrees of freedom, it approaches this, which is a normal distribution, while with a small sample or small degrees of freedom, it looks, something like this. So it's non-normally distributed. An investment consultant conducts two independent random samples of 5-year performance data for US and European absolute return hedge funds. Noting a return advantage of 50 beeps for US managers, the consultant decides to test whether the two means are different from one another at a 5% level of significance. The two populations are assumed to be normally distributed with unknown but equal variances. And we have the results of the test down here. Really quick side note, this is going to be done using a t-test, although all the information we need to either reject or not reject the null is already here. Should note that this is done with a t-test, which is used to test the difference of two population means. One other really quick side note, I highlighted the fact that the samples are independent, because if they are independent or dependent, there's two different formulas for the t-test statistic. So if it's independent, the test statistic looks like this. X bar 1 minus X bar 2 minus the hypothesized mean 1 minus the hypothesized mean 2 divided by square root of, and this is a little bit weird, we'll get to it in a second, S squared P over N2, where S squared P is like the pooled variance amongst, or the pooled sample variance between the two populations. The formula for this is, I have it in my notes, but highly unlikely that you'll be tested on it. Like the actual calc for this is, the formula is really long, but should just know that there are different t-stats depending on whether it's independent or dependent. I'll talk about the dependent one now. So this one would be, the test statistic is the difference. This is the average difference. It's a little bit different than subtracting the two sample means. So the average difference minus the hypothesized difference over standard deviation, sample standard deviation of the difference. This one's a little bit simpler. Small differences between the two in terms of what values you're going to end up with. But just know that, like I said, dependent versus independent matters, and you'll have different test stats either way. So coming back to the question, we have a sample size, we have a mean return for US and European managers, we have a standard deviation of each. The null hypothesis is that the population mean of the US returns is less the population of the European returns is 0, so they're not different, versus the alternative is that they are different. And we actually get our test stats right here. So they would have ran this formula here because it's an independent sample and came up with this 0.4893 value. And the critical value rejection points are plus or minus 1.984. So this test stat falls within the critical rejection points. So we are not going to reject the null, which is right here. Null is not rejected. B, you would almost think that it's the same thing. The alternative hypothesis is statistically confirmed. We never really do anything with the alternative with hypothesis testing. We only reject or fail to reject the null. The terminology never has anything to do with the alternative. And then C is that the difference in mean returns is statistically different from zero. This is the exact same thing as saying that we reject the null, but we are not going to. So this is wrong as well.
Here, once again, we're just determining which test to use in which scenario. So in this question, when evaluating mean differences between two dependent samples, the most appropriate test is a paired comparisons test, which is just another name for the t-test that we just described, where the null is at the difference of mean 0 and mean 1. It could be like 1 and 2, whatever. But the difference between these two means is 0, so our null is that they are not statistically different. And then the alternative would be, once again, that it's not equal to 0, which says that they are different. Anyway, just got to know that it's the paired comparisons test, which is the same as a t-test. Whenever you're dealing with mean differences, it's always a t-test. So one way to remember it. Chi-square test is most appropriate for tests concerning a single variance. Once again, touched on this a little bit earlier. And if we were to look at B and C, we're talking differences between population means, which once again would be a t-test. So both of these answers are wrong. All right, kind of bouncing around a little bit with the questions, but I think this one, the order that we've done kind of makes sense, and now we can wrap up. When to use all of the different type of tests in the CFA curriculum, depending on what we're looking at. So all we're supposed to do here is identify the appropriate test stat or statistics for conducting the following hypothesis test. And if applicable, also mention the degrees of freedom. So A, the null hypothesis is that the mean is 0 versus the alternative that is not equal to 0, where the mean is normally distributed of a population with an unknown variance, so it's automatically not the z-test, and the test is based on a sample of 15 observations. So this hits both of our criteria for the t-test, which is the answer, because the variance is unknown and n, the sample size, is less than 30. B, the mean is equal to 5. The null is that the mean is equal to 5 versus the alternative that is not equal to 5, where the mean is normally distributed with an unknown variance, and the test is based on a sample of 40 observations. So here, it's a t-test again. Even though n is greater than 30, we have a sample size of 40, we still don't know the variance. So not knowing the variance takes priority. If we knew the variance, it would be the z-test, but we don't know it, so we can't do the z-test, so it's t. For C, the null is that the mean is less than or equal to 0 versus the alternative that is greater than 0, where the mean is normally distributed with a known variance and the sample size is 45. So this is the z-test. If the if the variance was known but the sample size was less than 30, you would use t, but the z-test is normally distributed and the sample size is greater than 30, so we're all good. D, the null is that the variance is equal to 200 versus the alternative that the variance is not equal to 200. The variance is normally distributed and the sample size is 50. So here, kind of mentioned it a couple times, this is the chi-square, which has to do with one variance. We're only concerned about one variance. You'll see why that's important right now in the next one. So for E, the null is that the two variances are equal. So variance of 1, variance of population 2 are equal. And the null is that they're not equal. Don't even have to read the rest of this question. Whenever you're testing two population variances, the equality of two population variances, it's the F test. And if you'll recall from the last module, how I mentioned, like we had the chart of the F test, and we noticed that the degrees of freedom, there were two parameters for that. And that's mainly because we're talking about two different populations. So the F-test has two different degrees of freedom, has the degrees of freedom for population 1 and for 2. And then the last one here, we're doing mean differences. So once again, don't even need to read the rest of the question. It's going to be a t-test. And when you're dealing with mean differences in particular, it's called a paired comparisons test. And we can go back now and actually add in the degrees of freedom for all of these. So t-test with only one parameter. So the degrees of freedom is going to be n minus 1. So it's 15 minus 1 or 14 for this one. B, we're doing a t-test again with just one parameter, so we only have to subtract 1. So 40 minus 1, 39 is the degrees of freedom. C, z-test doesn't have degrees of freedom. There's no such thing, so that's not relevant. For D, chi-square is going to be n minus 1. There's just the one parameter, so 50 minus 1 is 49 degrees of freedom. For E, we're doing the F-test. And this is where the degrees of freedom is a little bit weird for the F-test. So we have the first sample size of 30 and the second sample size of 40. So there's 1 degrees of freedom for the first sample. So DOF 1 is equal to 30 minus the one parameter, so 29. And DOF 2 is the second sample size, so 40 minus the second parameter, so 39. And then finally, the t-test for the paired comparisons of the mean differences. Degrees of freedom is actually the sum of both of these two. So it's going to be 55 minus the two parameters, so minus 2, so it's 53. Here it's a little bit different, just kind of how the tests are structured. Like the F-test and the paired comparisons test both have two parameters that we're testing, so variance 1, variance 2, mean 1, mean 2. In the t-test, they're just grouped together, and then the degrees of freedom are subtracted together, versus the F-test where they are separated depending on the sample sizes. Last question here, we're actually going to do a chi-square test, and kind of what I said at the beginning of the module, I think it's pretty unlikely that this shows up on exam day, but we're going to do it anyway just to show you that the steps are exactly the same, and the only difference is how we're calculating the test stat and the value of the critical value. But like in this question, like it should be on the exam, the critical value is already provided, so the real only difference is the calculation of the test stat. So let's get into it. During a 10-year period, the standard deviation of annual returns on a portfolio you are analyzing was 15%. So we have standard deviation of 15. You want to see whether this record is sufficient evidence to support the conclusion that the portfolio's underlying variance of return was less than 400. So we're testing a variance, which automatically means just one variance, which means that we're using the chi-square test. If it was two variances, it would be the F-test. So in A, formulate null and alternative hypotheses consistent with your objective. So you gotta state the null and state the alternative. Remember, the alternative is kind of the opposite of what you would think. The alternative is what is in line with the statement in the question. So the alternative is that the portfolio's variance is less than 400, and the null by default then would be that it's greater than or equal to 400. Okay, so that's all good. And for B, identify the test stat for conducting a test and calculate the degrees of freedom. So we already said it is the chi-square test, but here we're actually going to need the formula for it, which is a little bit different, n minus 1 times the sample variance over the population, the hypothesized population variance. And here we have n is going to be 10-year period, so 10 minus 1 times the variance, so we have the standard deviation, but we need the variance, so it's 15 squared over 400 is our hypothesized value. And we run this out, and we get 5.06. So this is our test stat. Now the steps are all the same. So this is done, this is done. All we have to do now is compare this test stat to the critical value and see if we reject. So we have a significance level of 0.05, which doesn't matter because we're already given the critical value. This is what's really important. And now we have 5.06, which is our test stat, versus 3.325. And this is a left tail test, left, because if it's a one-sided test, it's worried about whether or not it's left or right, is worried about the alternative, not the null. You gotta remember that. So it's the alternative. So we would reject if our test stat is less than the critical value. So we're worried about the left-hand side. And in this case, we have a stat of 506, which is greater than our critical value, and we are not going to reject the null. Hope that makes sense. Like I said, I just want to show one of these different ones, like the chi-square F test, all that. Steps are exactly the same, just the formulas to calculate the actual stat is different, but concept is all the same.